you very much, Stefan, for the introduction. I'm Giorgia. I'm finishing my PhD at Telecom Paris. I'm working on neuro-steered source separation under the supervision of Slim Sid and Gaël Richard. But part of this work was done during an internship I did at Interdigital with Alexei Ozorov. In my thesis, I'm tackling the problem of music source separation, which is the task of isolating individual sound sources, which are mixed in the audio recording of a musical piece. Nowadays, we can say that often state-of-the-art models for music source separation are based on deep neural networks trained in a fully supervised fashion. Those models have been proven to be extremely powerful, but only if the amount of data is enough for training their parameters. And often it is hard for them to generalize to unseen test data with significant timbral variation compared to training. So we can say that music source separation is still an open problem for most musical instruments and music genres. One way to improve a source separation system performance is to use additional knowledge we may have about the observed mixture, right? So we can use, for example, the score, the lyrics, visual cues, and many others. And as well, the user feedback, which is one modality which is often underestimated, but is extremely powerful. Beyond manual annotation, the user reaction to a musical stimulus manifests itself also through many observable phenomena. For example, the heartbeat variability, body movements, and as well the neural activity. So in my thesis, I was interested in the latter, and in particular on the concept of selective auditory attention, which is the cognitive mechanism that allows humans to focus on a sound source of interest in a noisy environment. So this problem has been studied mostly for what it concerns the perception of speech in multi-speaker settings. It has been shown that the attended source neural encoding is stronger than the one of the other sources, and it can be tracked in the neural activity. So we can say that it's possible to decode the auditory attention to a source in the mixer, which means that we can actually say which source the person was focusing on by just looking at his brain response. This problem is known in the field as a cocktail party problem. It's not so straightforward to recast it to musical stimuli, because while in the multi-speaker settings, we have one speaker of interest, which is unrelated, let's say, to the background noise or other speakers. In music, the sources are playing in a coordinated way. And this makes both the decoding problem and also the separation problem more difficult. So in my thesis, I investigate if it's possible to use this selective auditory attention to drive a music source separation system. So our work can be divided in two main steps. First, we studied the problem of auditory attention decoding for music, and we show that for speech, our brain tracks musically relevant features which are more correlated with the attended source than with an unattended one. And then we investigated how to use this information to inform a source separation system. And we proposed one variant based on NMF and one variant based on deep learning. The brain response is characterized by EEG signals, which are particularly suitable for brain-computer interfaces because they can be acquired in a non-invasive way and they give a high temporal resolution. So let's start first with the data, because the problem had not been explored in the past, mainly because there were no data and it's very hard to acquire them. So I began my PhD by assembling this dataset, which is called MED-EEG, which was previously acquired at Telecom by a colleague, Gabriel Tregorat. The dataset consists of 20-channel EEG signals recorded from 8 subjects while they are attending to a specific source in music mixtures. The music we used is realistic music, are real music compositions, of which we have the ground truth sources. And they present many variants in terms of number, type of instruments, genre, and spatial rendering. The decoding procedure is usually twofold. Well, you first reconstruct an audio representation of the attended source from the EEG data using a decoder, which is a multi-channel Wiener filter, which is known in the field as backward temporal response function, because we go back from the EEG data back to the audio stimulus. This representation is then correlated with the isolated sources to determine which is the attended source. So the attended source is the one that presents the highest Pearson correlation coefficient with the reconstruction. And this filter is learned on a training set of solos and corresponding EEG data using a minimum square error criterion. So here we have some results. So we tested 3 different audio descriptors: the amplitude envelope, which is the one commonly used for decoding speech attention, and the magnitude-NMF spectrogram. And below you can see a table with the decoding accuracies. The correlation scores are very low, but this is normal. This is comparable to results with speech, but what we measure is the contrast. So in blue, you can see the correlation coefficients of the reconstruction with the attended source, in pink with the unattended source, and in orange with the mixture. So what we care is that the contrast between the attended source and the unattended source is significant, right? And the contrast is significant for time frequency representations. And for the amplitude envelope, it's not. So for music, it is necessary to have a more elaborated descriptor, which underlines amplitude envelopes at different frequency bands. And this is reflected as well in the decoding accuracies. The outcomes were positive. We could track attention also for music stimuli, and the contrast is significant, especially for time frequency representation. So it's possible to decode the attended instrument, even though these reconstructions are very deteriorated, and there is a very high intersubject variability, which depends mostly on the level of attention, but as well on the musical expertise and training of the listener. So then we investigated how to use this information to inform a source separation system. As you have seen, the attention decoding problem and the source separation problem are naturally related, because to decode the attention, we need the ground truth sources to correlate them with the neural data and say which is the attended source. Previous work for neuro-steered speech enhancement, the 2 tasks are tackled sequentially. First, the separation system provides the reference sources for the decoding, and then the decoding system selects the source which needs to be enhanced. However, tackling the 2 problems sequentially might be suboptimal. So the first variant we propose is a variant of non-negative matrix factorization, which is a technique for data decomposition that it's quite popular in audio inverse problem, because it allows to unmix superimposed spectral components. So we can represent the audio with its magnitude spectrogram and decompose the spectrogram into 2 matrices, W and H. The columns of W can be interpreted as spectral patterns, and the rows of H as their activations. In this picture, you see the case of a single source, but when you have multiple sources, then the separation problem reduces to the assignment of each of these components to the right source, in order then to use the learned representation as a source variance model for the Wiener filter. However, this decomposition can be tricky for complex signals like music, because usually one source plays multiple pitches, and it's hard to represent them with a single component. So it's hard to get a good decomposition in a completely unsupervised way. So what we can do is we can use additional knowledge we may have about the sources to guide the decomposition. This can be done by directly integrating in this optimization cost, regularizers, pre-trained dictionaries, hard or soft constraints. In our case, we have the information about the contrast between the attended and the unattended source, which we can derive from the EEG. So we propose to add to the unsupervised formulation this additional term, which imposes that audio-derived activations of the attended source should be similar to the ones I can derive from the EEG, and at the same time, the audio-derived activations of the unattended source should be dissimilar. So in practice, we learn a projection that maximizes the discrimination capability of my decoding model. In the algorithm, the factorization and the TRF model are learned jointly. So first, we reconstruct the activation of the attended source from the multi-channel EEG-R using a pre-trained TRF model. These activations are used to guide the factorization with the proposed C-NMF variant. And after a certain number of NMF iteration, we can update the TRF model using WA, which is the dictionary associated to the attended source, and using it as a new feature extractor to retrain the TRF model. So after convergence, we will have a dictionary WA and its activation HA, which can be used to recover the attended source. So here are some results. In green, you can see the proposed method informed with the EEG information. In blue, you can see the blind NMF, so the completely unsupervised NMF. And in orange, you can see the proposed model, but informed with random side information. So this was done because we wanted to see which was the effect of the contrastive formulation and which was the effect of the EEG data. The EEG-informed model is statistically significantly better than the baselines for all the instruments except for the base, for which the difference among the methods is not significant. The main outcomes are that we could improve the separation, especially in difficult cases, and we had an automatic separation of the attended source, which means also that we could do auditory attention decoding without the need of the reference sources. Still, we have the problem of the high intersubject and intrasubject variability. Using the user feedback to inform a source separation model was widely explored in the literature, mainly for what it concerns NMF or NTF-based source separation systems. It is less explored for deep learning because in practice, usually those models are learned using both the side information and the audio material to be separated. This means that you need the side information also during training, and especially when working with EEG data, it's hard to have data sets which are big enough to learn a deep learning model from scratch, which contains also the EEG annotations. What we propose is a user-guided one-shot adaptation for a deep learning model for source separation. So it means that we want to take a music source separation model based on deep learning, which is maybe a state-of-the-art model, which was already trained by someone else, which works very well, but maybe on one mixture is not working perfectly, and we want to adapt it to this specific mixture. So the adaptation is one shot because it acts on one test instance only and not on a data set. We do this adaptation using some side information, which in this case will be the time activations indicating where instrument is active. So usually a deep learning based music source separation model working in the waveform domain is trained by comparing the ground truth sources with the estimated one. During adaptation, we had access only to the activations annotated by the user. We proposed this adaptation loss, which is very simple, which aims at reconstructing the mixture and minimizing the energy of the silent sources. For the experiments, we choose a state-of-the-art model working in the waveform domain, which is ComTestNet, and we adapted it on the test mixture for 10 epochs using 4 seconds long segments extracted from this mixture. We tried multiple fine-tuning strategies in the sense that when fine-tuning a model is often useless to fine-tune all the parameters because, for example, the first layers may extract some general features which are useful also for the new task. And in our case, we don't even have a new task. We have only an adaptation on a specific test instance. So here you see I numbered the blocks of the network because we fine-tuned up to a certain block in the experiments. We first decided to work in a controlled scenario. So we imagine that the user is manually annotating the activations. So we choose the MUSDB dataset, which was the same dataset on which the model was trained. And we computed the activations on the ground truth sources. In the table, you can see the SDR results for different fine-tuning strategies compared to the baseline, which is the non-adapted model. And in the figure, you can see the same results, but compare as well to these orange bars, which represent a completely unsupervised adaptation. So it means that we just have the mixed reconstruction loss. So we can see that the results actually improve for all the instruments except for the vocals. Once we validated that our proposed loss function was working, we moved to the EEG data, from which we can reconstruct time activations, which are much more deteriorated. So as before, we used a decoding model to reconstruct the amplitude envelopes of each source from the EEG, and then we binarized those amplitude envelopes. And here are some results. Now the improvement is not systematic for all instruments. We improve only for other and base. In the figure, you can see in pink the activations reconstructed from the EEG compared to the activations computed on the ground truth sources, which are the green ones. So yeah, the results are not great, but the mixtures in the MED-EEG datasets are not ideal for this study because first of all, the mixtures are quite easy to separate. So you see the B0 baseline is already performing extremely well. And secondly, the sources are almost always activated. They tend to be always activated. For example, here there is an example of guitar, and you can see that it's always activated. So this leaves small room for action for a loss based on the activations. But yes, we are working to improve this work. So the main outcomes is that we could do adaptation directly at test time, that we could do auditory attention decoding without the ground sources, with only a small degradation of the performance compared to the decoding performance we obtained with the ground truth sources. And that this is a very general approach that can be applied to other tasks, modalities, and deep learning architecture. However, yes, there is this limitation that the sources cannot be always activated. So to conclude, here I put the references to the papers. I would like to say that MED-EEG, the dataset, is publicly available on Zenodo. So if you want to try to work on it, yeah, it's publicly available. Thank you very much for the attention.